Um, all right. Can you see my screen? I mean, you can send me in the chat. And I would request from Sci Expert, someone please, and I mean, admit those people who are already in the queue, because I can see still many people are trying to join the session. And I am admitting. Okay, or from size part, if someone can do that would be great for me, and I can start. All right. Okay. So good morning, everyone. And my name is Sabiha Gulshan. I did my bachelor's and master's in statistics, and then I also did my master's in demography from Stockholm University. And now I'm working in Linköping University as a data analyst. I work actually with the adult education, and yeah, that's it all about me. So today we are will work about the practical second practical application of Stata for data management, econometric modeling, and diagnosis and time series analysis, panel data analysis and reporting. Please note that this session, I mean, this today's training program is only for 3 hours, and we have half an hour's break. So it was not possible to cover in depth, but I tried to include some econometrics, data structure and modeling, and also model diagnostics. What we are going to cover today, um, as I will be going through that. And please note that this is intermediate level, so I'll not be going to too basics. So people who have some familiarity with statistics and quantitative methods and fundamental knowledge will be helpful for them. And this also uh, also remember that we will, I mean, our participants are from the universities, our public institution, or commercial organizations. And while all examples will come from economics, business, and public policy, the techniques we cover can be applied across wide range of research and analytical setting, and a basic understanding of statistics and some familiarity with the statistics will be helpful. So far, I would like to see if there is anything in the chat. Will the session be recording? Yes. Uh, I think Sci Expert is conducting this training program, and they are already recording. And after we end, it will be shared with you. Also, one more thing I would like to say, that you can see in the chat, they have shared already the training material. That means the presentation I'm using is uploaded, and also the do file is uploaded. Though we will be doing all the command, all the syntax is there already in this slide, and will be working uh, in the Stata, and I'll show you when I start. Okay, is there any question so far? Throughout the session, if you have question, you can raise you can raise the hand, or you can write in the chat that I will address maybe at the end of the session, or during the session if possible. I'll try to address your questions. But as you know, the time will be short. Maybe sometimes I'll be going fast, and you also can ask questions after the session, and send me email me or a Psi expert, and I will be replying. Okay. So now we move to this, that what we are going to do first. After completing this training, I think you should be able to know or see what is your data structure, or knowing the different types of data used in econometrics. And we'll also do regression analysis and setting models. And not only that, we'll be going for the diagnostics, model diagnostics, and then we'll move to time series and panel data. And I have included only one small slide for reporting and automation that most probably you know already, that how to open the do file, how to save your work in the log file, and also how to export or import tables, regression tables, or the graphs. And the session is divided into two sessions. In the first session will be 9 to 10:30, and where we are going to cover the types of data, regression models, and model diagnostics. And then we'll have 30 minutes break from 10:30 to 11. And in session 2, it will be only 1 hour, 11 to 12, where we're going to do model series, panel data, and reporting. And there I can see some people are still trying to admit. Okay. Okay. I also think that yes, there is someone is asking a question. Uh, I'm not sure how to download the product because of the fields username and password which are required for the registration form. I am not sure that which product you mean. I don't understand. Can you unmute yourself so that I understand that we are trying to download the materials or the Stata? Iona Ivanova. Can you unmute yourself and let me know? Hello? Oh, no. You don't see the full screen. Yeah. Okay. Let me see. Is it better? Okay, so you have to download the Stata, and I really don't know how to solve that matter, because you need to speak with the expert people. They have, I think, sent you a link for the participation, and you need to download that. So I think, yeah, you need to go through the software, license details, the serial number, and all these things, details, people who are. Yeah. Okay, and about all others, can you see the, I'll try, thank you, can receive an email. Okay, the screen is okay. Um, Okay, and also when I will be using Stata, that time I'll be minimizing this or making it shorter, this presentation. But for your convenience, I have uploaded in Google Drive this presentation. So if you can't see my screen, I think it doesn't matter. You can open this presentation uh, in your desktop or laptop, whatever possible. Okay. All right. So now I don't understand what is the bottom at the right corner. What do you mean by that? Okay, license. Okay. Anyway, uh, oh, okay. So you cannot unmute yourself or speak. So you can put the chat in the chat. Okay. So if everyone can see the screen, and then I can continue. Is that okay? Just if everything is fine with you, you can see my screen, and then I can move forward. Okay. Um, we do not see the full screen, but all of the slides and the notes. Which one do you mean in your PowerPoint that I have uploaded for you? Only the difference between the PowerPoint and for the participants and mine. In mine, I have just added some notes, and I have taken those notes for for the one I have uploaded. So it's nothing, but I tried to include as many details as possible in the slides, so you don't need to bother about the notes at the end. But if still you would like to see my notes after this session, I can upload with the notes also. But you will let me know at the end. But I tried to include everything. Okay. So let's start. As I already said, there will be two sessions and there will be half an hour's break. And at the end, there will be QA, question and answer. But you can ask also questions throughout the session. But because of the time limitation, I may not answer at the moment. I'll try to do that at the end or throughout the session, or maybe after the session. All right, everything is okay. Please continue. Okay, thank you so much. Okay, so this is the session one. We are going to see data structure, regression analysis, and model diagnostics. Please note that because this is a bit, I mean, intermediate one. So I am not including all the basic ones like of Stata that I already covered with SciExpert several times before. You can, if you need the basic one, you can talk to them, and they must be having some videos. Okay, so first what we would like to see, we would like to know the data structures of economic data, especially because this we are focusing more on economic data. So now before estimating any model, we first need to understand the structure of our data. In econometrics, we commonly work with three types of data that you can see here. Cross-sectional data that contain many observations collected at a single point in time, such as household survey conducted in 2025. And then we can see the time series data, and time series data follow one unit over time, such as monthly inflation rate or GDP of a country, something like that, stock prices. And then the most important, I mean, or frequently used is panel data or longitudinal data, where it combines the multiple units observed over multiple periods. For example, the country observed annually over the 20 years. So what we would like to see, that distribution is important because the choice of econometric methods depend on heavily on the data structures. Methods appropriate for cross-sectional data may not be suitable for the time series or panel data. So we need to keep in mind that the structure of data determines the appropriate econometric methods. I can see something in the chat. And oh, okay. So the next one, again, I wanted to explain a bit more about the data structure. So first, when we talk about the cross-sectional data, I have included an example here where you can see that here we observe the different household. That's household number 1, 2, 3, 4. All are different household. And they are observed at a single point of time. In this case, we are considering for 2025. Each row here represent different household, and the column contains characteristics such as age, then education, income, region, and etc. Cross-sectional data are commonly used in household surveys and also labor market studies, customer analytics, or many social science applications. Okay. Now, we can move to the next one. After cross-sectional, we'd like to get a brief idea about the time series data. So here in this example, we can see that instead of observing many units, we observe one unit repeatedly over time. So here the national economic indicators like GDP or inflation rate, unemployment rate, or interest rate have been observed in different years from 2019 to 2020. So one indicator has been observed in different time period. So time series data is particularly important for forecasting, trend analysis, policy evaluation, or making them widely used by government, central banks, or financial institutions. And the last one that I would like to give the example is panel data examples. So remember that panel data combines both the cross-sectional and time series dimension. In this example, we observe that multiple farms like farm 101 and 202 have been observed over several years, like 2022, 2003. So each farm has been observed for 3 years. 3 years. This structure allows us to study differences between the farms as well as changes within the same farm over time. Panel data sets are very powerful because they enable us to control the unobserved characteristics that remain constant over time, which often improves the quality of our analysis. Okay, and I can see any more chat. I can see what. Okay. All right. So after we know this different, three different structure of the data, we can choose the appropriate analytical method. Cross-sectional data sets are often analyzed using the regression models such as OLS or ordinary least square regression, and then logit or probit, and that will be doing that in the following session in forward. So time series Time series data typically are forecasting uses. We use forecasting methods such as ARIMA, and panel data set commonly use fixed effect and random effect models. The key message is that the choice of statistical method should always be guided by the structure of the data. Now we understand the main types of data encountered in empirical analysis. Let's move to practical side and explore how Stata help us to manage and clean and prepare this data set before conducting statistical analysis. Is there any questions so far? We didn't start anything with Stata though. Okay. Now, in this section, I'm going to the regression analysis and the model diagnostic. So first we'll be starting with linear regression models, particularly ordinary least square, and we'll be focusing also interpreting, because setting model is easy and also finding the output is easy, but it's very important that we understand the output. And once we are done with linear regression, then I will be doing the model. We'll be going for we'll be going for the model diagnostics, which is with the multicollinearity testing or heteroscedasticity testing, robust standard errors, and all other things to see which model is appropriate for our data structures. And we will also touch very briefly, not very details, the binary outcome model and count models, but because of the time limitation, again, I couldn't go into depth. Okay. So to start with the ordinary least square regression model, remember that OLS estimates the relationship between the dependent variable and the one or more independent variable. So in this example, what we are going to do to explore or to understand how vehicle price will be associated with this fuel efficiency or the weight of the car, or whether the car is or the vehicle is domestically produced or foreign make. So here our objective is to estimate how fuel efficiency and weight and foreign status are associated with the vehicle price. So to do that, we are using a data set from Stata inbuilt data set, and here we are going to start using the data of Stata. So I'm going to minimize this, and you all have this slide with you so that you can refer every now and then. This is my do file, but I'm not going to use this do file now. I will be copying and pasting the Stata code from the slides so that you know how it happens. But for your reference, I already have uploaded the do file also for the session, and you can use that afterwards. But all the Stata codes that I I have in the do file are also in this slide. So for our training purpose, I'll just copy and paste these codes and see whether it works or not, and I'll try to explain these things. So first, let us download this data set. And remember that we're using the data from Stata inbuilt data, and for that we use sysuse auto. So the data set is auto, and let's this data set contains when we can see the details in this area, but I will use this describe command to see the data set or to explore the data set. So we can see that these are the variables included in this data set, make, and these are the variable labels. That means make is make and model, and the price, mileage, or fuel efficiency, you can say here, and repair record. Since I mean, these are the variables of interest we have include the data set includes. And also, we can use the summarize command to explore or know the data a bit more. I'm sorry. So, can anyone say what mistake I did here? You can unmute and you can tell me. So, what mistake did I do? Missing S, yes, thank you. So, I mean, Stata is very much case sensitive, but if I used instead of summarize, I could start only the first three, one, SUM, Stata understand. It would give us the same output. And also the first one, I used the description. So describe, instead of describe, if I use this, I would get the same thing. So Stata is case sensitive, but you can use the first three later, maybe for the short form. And we also can see the data itself, because before we start, we are going to use this auto data today. It's better to have a look at the data set with the browse command, and where you can see these are our variables, and make is a string variable, you can see. And all this, I mean, these colors, already you probably know that colors different. One is having different color because this is our string variable, and these are the uh, qu quantitative variable or numeric variable, sorry, and this one is categorical variable. So that's it about little explanation about the data sets. And with this data set, you can see that we can also use our tabulate command to see that what does the foreign means here. We can see that there are two value label here, domestic and the foreign, and about 70% of our vehicles are domestically produced, while 29 or around 30% are foreign made. I can see someone is writing in the chat how to put data set into Stata. Okay, you can do in a different way. One is from here. You can, because today I used from Stata inbuilt, so you can go for example data set here, and here you can see that there are a lot of data set there, so you can do use from here. So this is inbuilt data set. But in case you would like to upload data set from your device, in that case you would be going to file and then import data. You can also upload or load data in Excel, or you can do the CSV file or text delimited. So also you can do SPSS, SAS, or different options are there. But because this I cover usually in the basic, so I didn't include this part in Stata. But you can do from here Excel, and it takes you, like, you need to go to anywhere where I have Excel file, because I don't have right now in my device. But if you have the Excel dataset, you just click on it and then open, and then it will be downloaded. So I'm canceling for the moment. Is that okay? Yes, sysuse, we are using sysuse auto because this data comes from Stata software. So you need to use sys use. But in case we used from our data, then we use that we can put in our drive, and we can use only use. Um, Before that, I also forgot one thing. Before you start any session, you should choose a directory. So you can go to File and then change Work Directory and choose the place where you would like to save your work. So you can write here choose, because for me, I have made the day one. This is my day one session, and day after tomorrow I have day two session. So I have the folder and I choose it. So this is my folder. You also can do the same. You can download all the materials and keep in the folder, and that can be your um, Stata session. Another thing you can do is you can open an do file, so that you can type everything yourself here. So when you open a do file, always better write version. I'm using 19.5, and then you start like, for example, our first code was sys use and sys use auto. I mean, you can write your codes all here, but already we have in our, someone is still cancel, because I already have it, so I don't want to save it or delete. Okay, so I already also, you can open the do file that I uploaded already. So here, always is better to include your version number in your do file, and then clear all. That means I don't want anything what is there, so everything should go off. Set more off also. um, so I always prefer to keep these two next to each other. And how can you run these codes? I'm sorry, I'm just still struggling to keep this. Screen is so small. So when you are in your do file, after opening, you can just set more off. I mean, click from here, do. And I already showed you that you need to set your work directory, and you can open also do file from the existing, or you can open a new one with this command. I kept it with, when I put this star sign in front of the code, that means it understand that this is just comment, and they are not going to execute this as a syntax. You also can open a log file. So where can you open the log file? File here, and then log, and then begin. And what happens, you need to give a name. Maybe I'll write here day one. Sorry, day one log. Okay. So what the log file does, whatsoever work we do, all the outputs and command will be saved in log file. That can be your future use. So that's it. As I said, that I'll be copying and doing from here, so that we can see that all our code works, and you can ask questions in the meantime. So I'm going to do from the beginning. So this is our data, auto data that comes with the Stata website, or inbuilt one. So we also see that what are the variables it includes, what's the details of the data set. You can notice here you can notice here that make is a string variable and the price, mile per gallon or the mileage, and all these are integers or numeric data, and foreign is a categorical data. So now, after we have summarized and we have seen little about the data, we are moving to OLS. That, as I said, that setting model is easy, but we need to understand that what this model says. So we need to explain the, we need to know the output interpretation. Okay. So from here, what we can see that from R square and R square 0.49 or 0.50, right? And the model is you can see the p-value. The model is statistically significant. And also we see that these are the variables here, and weight is uh, positively predicts the price, and it's statistically significant also. And we can see if the car is made in the foreign compared to the domestic car, is more expensive than the domestically produced car. And also we can see the fuel efficiency here, or MPG, is not statistically significant from this p-value we can see here. So what we can conclude from this OLS or regression model, and that a heavier car tends to have a higher price. And also we can see the foreign cars cost approximately more than 3,000, and then the domestic cars, holding the other factors constant. And also we can see the fuel efficiency is not significantly associated with the car price because of the P here. And then we are going to see the robust standard error. Another thing I would like to see mention here, that what R square here denote that overall model is statistically significant and explain about 50%. I mean, for 0.4996, that means 50% of the variation in the car price. So that's all. And looking at the coefficients here, already I explained the vehicle weight has a positive and statistically significant effect on the price. We also, okay, and another thing, already we said the foreign born or domestically born, and weight, we said that heavier cars tends to be more expensive, and foreign made car is more expensive than domestical one. And in contrast, this is not a statistically significant, be careful here. So now we want to do the re-estimate the model using the robust standard error. Okay, so for the robust standard error, we are going to copy again. Let me know if your code doesn't work, because I may make mistake. Finally, when we look at this, notice that the coefficient estimate remains exactly same. You can see that without robust standard error, the coefficient remain the same. But what changes actually? We can see the changes in standard error, and also we can see the changes in the t-value here. So estimate doesn't change, but our standard error and t-value changes. What does that mean by that? The standard errors and t-statistics change slightly, giving us inference that is more reliable when heteroscedasticity may be present. So it gives us a signal. And any questions so far? No. So now we are moving to the next one, detecting the multicollinearity. So after estimating our OLS model, we should always perform diagnostic tests to assess whether underlying assumptions are reasonable. First, we examine the multicollinearity using the variance inflation factor, or VIF. So here is the code we are using, but most, one second. Yeah. So what does this means? First, when we do this VIF, we see that multicollinearity occurs when the explanatory variables are highly correlated with one another, which can inflate the standard errors or make coefficients. A common rule of thumb you can check here is that VIF values is above 10 may indicate serious multicollinearity. But in our model, we can see none of them are more than 10, and the mean VIF is 2.81. Therefore, we can conclude that multicollinearity is not a major concern for our existing dataset, this auto dataset. Next, we test for heteroscedasticity using the Pagan and Koch-Vespers test. The null hypothesis here assumes constant error variance. Our test produces, so let's do the next one, this together. One thing I want to notice that, although you may ask me here that why am I copying the regression model again, because I have already run this robust standard error. So after that, if I want to do the heteroscedasticity, it won't work. So you need to run the regression model again. So what we see here, our null hypothesis assumes constant error variance, and our test produces a p-value is 0.0118, which is below 0.505. Therefore, we reject the null hypothesis. And conclude that heteroscedasticity is present in the model. So when heteroscedasticity exists, the OLS coefficient examines remains unbiased. But the standard errors can become unreliable. A common solution to re-estimate the model using the robust standard error by adding the VC that we have done before. So you can run the same code if you want. Okay, so that's it. And do you have any questions so far? I can see some people are still trying to join. I'm sorry for the people who are already there, and it's irritating when I have to pause all the time. Okay, so now we can move to the next one, the residual analysis or model checking. So why examine the residuals? Because we need to assess the model. We also need to see the whether heteroscedasticity presents or not. We need to identify the outlier and influential observations, and we need to check the model assumptions. I can see. You can use robust standard errors, Elena. Okay. So now we are not going, yes, you can use that term standard error, robust standard error, to improve the model. Now we are moving to the next one, residual analysis and model checking. So for that, we can go for this. You also can do the residual analysis and model checking. People who are asking the question about this. Yes, and then we are going for the residual analysis and model checking. So here we can have a visual picture. So in the residual analysis, it helps us evaluate whether the regression assumptions appear reasonable. In particular, we look for evidence of heteroscedasticity and non-linearity and influential behavior. Like, so people who are asking that what is the remedy for the heteroscedasticity, you can do the residual analysis and model checking. So in Stata, we first generate residual using the predict command, and then create a residual versus fitted plot using the RV plots. Yes. So here, ideally, we would like to see a random cloud of points centered around the zero with roughly constant dispersion across the fitted value. However, our residual plot does not show that pattern here. The spread of residual becomes larger for the higher fitted values, indicating that the variance of the error is not constant. We also observed that several observations with unusually large residual, which could potentially be influential point. These visual findings are consistent with our earlier test, which provided statistical evidence of heteroscedasticity. So therefore, although the OLS coefficients estimates remain unbiased, the usual standard errors may not be reliable. This is another reason why we use robust standard error is recommended for this model. Is that okay? People who are asking those questions about the remedy for the heteroscedasticity, so it's better to use robust standard error. So that's brief about this. Now we are going to briefly include limited dependent variable models, for example, binary outcome model and also count outcome model. So as I said that in only 2.5 hour sessions, including very vast detail, is not possible. So I tried to touch the basics basically of the commonly used econometric models for econometric data. So now in our limited dependent variable models, the first one we're considering binary outcome model. So first one is logit or logistic regression model. Here, in logistic regression is used when the dependent variable has only two possible outcomes. In this example, we study whether an infant is born with low birth weight or not. The dependent variable called, so we are using the data called LBDT here. So we'll be using the stata command soon, but you can use the data set from here. This is the command in stata to have a look in our data set. So copy. So now we are using the data set Hosmer and Lomesho birth weight dataset, which contains information about 189 observation. How can we see that? You can describe and see the variables. Describe. I don't want to use simple because simple will give you only the variable names. So these are the data set. You can see observe 189 and we have 11 variables, and these are the variable names and the variable levels you can see. So what we also can see that our here we are thinking about or our research question is, do mother's age or smoking status and race influence the probability of low birth weight? And for that our variable of interest is low. So let's tabulate it and see that what does it low means here. So here the children bought or an infant born, sorry again. Okay. At the birth, if a child's or infant's weight was less than 2,500 gram or 2.5 kilogram, we can say, so they are considered as low. And so here we can see that around 68.8% have normal weight and about 31.2% have low birth weight. Okay. All right. And now if we move to the next slide, where we use the stata command. So we're going to set our logistic regression model. And as I said that this is binary model, that means our dependent variable has two outcome, 0 and 1. So the infant born with normal weight are 0 and born with low weight are 1. So we are, based on our research question, we are going to set our logistic regression model that comes here. And we estimate here the logistic regression model using the maternal age, smoking status, and race as the predictor of low birth weight. So here in the model we have included, this is our dependent variable or outcome variable, and all these are our independent variable or the predictor variables. So what we can see, the overall likelihood ratio is statistically significant because our p-value is much lower than 0.05, suggesting that the predictor collectively improve our ability to explain the low birth weight. And looking at the individual predictors here, these are our predictor variables. Smoking, when you go to here, smoking is strongly associated with low birth rate. With a low birth rate, the coefficient is positive and highly significant, indicating that the smokers have a higher probability of delivering a low birth weight infant. Okay, and we also can see here the race. Race is an important predictor here. Both the black and the other racial groups have significantly higher, you can see one point is, that means higher, and the positive effect, higher probability of low birth, giving birth of low birth weight infant compared to the white mothers. And we are going to look at the age. We can see maternal age, however, is not statistically significant. You always look at the p-value here. So it's not statistically significant in this sample. So because logit coefficients are expressed in log odds and are difficult to interpret directly, we often use the margin command to convert the result into the predicted probabilities. So let us do this margin command to understand our output in a better way. So looking at the individual predictors here, smoking is strongly associated with the low birth rate. Again, you look at these p-values here. The coefficient is positive and highly significant, indicating that smokers have higher probability than non-smoking mothers. Okay, and the race again is important predictor. I think I have already included. Okay. Now, with this, once we have this, that we can see that race and also is a strong predictor for the low birth weight, or is a factor. Now we are going to have a visualization. So let's check. Yeah. So the figure here shows the average predicted probability of the low birth weight. You can see here, these are the predicted probability. So once when we can see for the lowest predicted probability for the white mothers who are from the white background or race, and the highest for the black race, and the others is also much higher than white category. Um, yes, it's possible to download this link. Is shared already in the drive do file, and also the presentation, so you will be having access to both. Okay, thanks. So after the model and the output and the visualization, what we see here, the smoking substantially increases the probability of low birth weight, and the black and other racial groups exhibit higher predicted uh, probability, and the maternal is not statistically significant in this model. So predicted probabilities and confidence intervals are often easier to interpret than the log odds coefficients. Like there is possibility to change into I mean, in the other measures, but I did not include that. So it's better always to look at this. We can see another visual things that I don't have any explanation here, but I just kept it so that you can have a visual idea. Yeah. So I have tried to differentiate between the two categories, non-smoker and the smoker category, to see how it affects. So in both the cases, we can see that compared to the mothers from the white race, both, I mean, black still in both the groups have the higher predicted probability of giving low birth weight child, and in both the cases, though for the non-smoker, uh, I mean, is little less, but for the smoker is much higher. And even when we look at this white background for the smoker and non-smoker, the smoker have higher probability to give low birth weight children for all the same. I mean, all you can see for the black also higher probability for the smoker group, and higher probability for the other category as well. how can we save work done in Stata until okay, present moment, including the graphs? Yes, I will include that how to save your work at the end. And also you can do save that. I showed you how to open a log file. So in the log file already your all the codes and all the work that you are doing are saving. Another possibility that all these codes after you are done you can transfer and you can save in a do file. Okay, is it possible to upload the presentation with comments included? The PPT does not include the comments, which is so important. Yes, I can do that. I just didn't like to bother you with so much of things because I add lot of comments so that I don't forget something that should be said. But if you want, after this session, I will upload in the same folder and you can get that. Elena, is that okay? Okay, Elena, and who else? Dana. I will upload my slide with the comments in the same folder, so you can access it after the session. And it's the same thing, but I'll just make the file name with comment so that you can see speaker comments. Okay, you're welcome. All right. So now we are in the binary model. I'm sorry. We have the logit model here. Okay, now we are moving another type of binary outcome model that's called probit model. And what is a probit model before we move for setting model here? Here also the data or the dependent variable or outcome variable is binary. That means it has two values, 0 or 1, and it estimates the probability of an event occurring. And it assumes that standard normal cumulative distribution and usually produces results similar to logistic regression that we are going to see. We have used the same data set that we used for the logit, so I'm not going to explain again because we already have the same data set, but I'll be using only the command for to show you the output in the probit. So this is the command that we are going to use to set a probit model. And when we move upward, we can see that the result or the coefficients almost remain same. You can go up and see that for age we had 0.0218 and we have this, no, logic is little bit different. Did we use all these things? Yeah. So we estimate here that again, when we look at this likelihood ratio test, statistically again significant because we look at the p-value here less than 0.05. The model helps as a whole help explain to low birth weight. Smoking is strongly associated with low. Again, we can see smoking is strongly associated positive effect, we can say. And the average marginal effect indicates that the smoking increase and probability of the low birth weight by approximately 20. But for that one, we're going to see the margin effect because it's difficult to what is say interpret this because so it's better always do the predicted value or marginal. Sorry. Yeah, so here we can see the average marginal effect indicates that smoking increases the probability of low birth weight by approximately 23 percentage point. Yeah. And race is also important compared to black and the other, compared to white, the black and the other group exhibits the probability of low birth weight, that is roughly in this case 20%, and this is 21% higher than the white mothers. Okay, and the in this case also the maternal age is not significant, statistical significant, and notice that this conclusion are almost identical, because whatever we saw in logistic regression model and probit, or I mean almost the same things we are getting, right? In practice, logit and probit models are often lead to very similar conclusion actually. Okay, so that's the very brief introduction of logit or and probit, the binary outcome model that we are going to use when we have outcome model, outcome variable, a binary, 0 or 1, that means pass or fail. Then also maybe low weight or not. So success or failure, some employed or unemployed. So these are the different occasion to use them. Now we are also going to touch briefly the count outcome model. Um, so, count outcome models are used when the dependent variable represent count rather than continuous measures or the binary outcome. So, we use what is the continuous? There are some example you can consider. For example, number of deaths, number of hospital visits, or number of accidents, number of publications, or whatever. So here our outcome values are non-negative integers. Okay, and we use a different data set that already we used before also, from I think the same data set. I'm not sure. Are we? Yeah. So we use the Dole and Hill mortality data set, different data set that records the number of death and smoking behavior, age categories, and person years exposure. The research question that we are going to consider for this example is whether mortality rates differ across the smoking group and the age categories. So we'll begin with the Poisson model. So there are two commonly used, we can say, Poisson and the negative binomial models here. But remember that both the model has assumption. So what are the assumption here for the Poisson model? Assumes that the mean and the variance of the count variable is approximately equal. And if the data exhibits the over dispersion, that means they are not equal, where the variance exceed the mean, then the negative binomial model is more appropriate. So it's very important when you are dealing with the count outcome model. So we will start with Poisson with this assumption. If we see that this assumption is violated, then we'll be going to negative binomial model. So these are the characteristics of our data set, but before that, I think I need to show you the data set by uploading the data set. Today, I tried to include all the data set from Stata inbuilt data set because I didn't like to download the data set. Some people may not access, and yeah, so this is our data set, and I go back here. What are our variable of interest here? we can see that number of death here, and also age category. This is age category, and P, this is person years at risk. And so there are 4 variables we can see in this data set. So now when we set the portion model, here what our research question we are considering that do smoking status and age influence the mortality rates. So keeping that question in mind, research question in mind, and also having the data set outcome variable count, we are going to set our first portion model. So here the result indicates that the experience approximately for smokers experience approximately 43, you can see here, I mean approximately 43, or you can say 42.5 or 6% higher mortality rate than the non-smokers, and the result is statistically significant. You can see here the p-value is less than 0.05, and margin output translate this finding into predicted counts. We expect around, so here we are going to do the margin and the margin plot so that it will be visually we can interpret in a better way. Okay. So margin output translate this findings into predicted counts. We expect around 54% here death among non-smokers and approximately 77 death among the smokers. I can see some chat. Okay, Elena, let me see. Someone is asking about the data set. Actually, I took all from the Stata inbuilt data set. So when, for example, I'm using, one second, yes, this is the data set. So when you use this and clear, then by default you get the data set. It comes from Stata website. Is that okay? Yes, Andrea. Okay. Now we move to, yeah. So 54% death among the non-smokers, and we also can see that approximately 77 death among the smokers. Okay, so we also estimate the negative binomial, but before that I would like to do the margin plot. Okay, so clearly seen that no, here in the figure, you can see, but okay, I'll come back to the figure because I want to show both the figure in for both the model afterwards. So now after we set the portion model and we have seen the results or the output, now we are going to do our negative binomial model. So okay, So what we see here, negative binomial model, the estimated over dispersion parameter is essentially 0. And you can see here, this is 0. So over dispersion is 0, alpha. And likelihood ratio test is not significant. So let's go to our likelihood ratio. It's not significant because of the p-value. Here you can see 0 0.5, where it should be less than 0.05. So it's not significant. Therefore, there is no evidence of over dispersion, and that means that simpler Poisson model is adequately describe this data. So because we already said before that Poisson model assume that mean and variance are approximately same. When this assumption is violated, that we are going for the negative binomial model, but this alpha value 0 shows that actually our Poisson model is appropriate because it doesn't violate this assumption. Okay, so coming back to here. And now, one thing I wanted to show you, that if I do this for the Poisson model, if I want to plot the margin plot, you have this what is a predicted margin of a smokers at 95% confidence interval. Now I'm going to do the same thing for the negative binomial margin plot, and I would like to see what are the difference we find. Okay, we can see that same thing has come, same image or visualization. So we notice that here that two figures are almost identical. This is not a mistake actually. The negative binomial model estimated almost 0 over dispersion. That means alpha value here is 0, and so effectively reduces to the Poisson model. In practice, we would report the Poisson results because the extra uh, flexibility of negative binomial model is unnecessary here. So when we are choosing the model, we always have to see here that when you have the outcome variable continuous, then for example, income, wage, and then GPA or house price, we use OLS. When you have binary outcome model, outcome variable, then for example, employed, unemployed, disease, no disease, success or failure, and also death or low weight or not. So we use logit or probit. And for the count data, you can use number of visits. For example, number of visits or accident or publication, we use Poisson or negative binomial. But one thing we always recommend in statistics, that when your assumption is not violated, then Poisson should be chosen. But when it's violated, then we are going to go for the negative binomial. Uh, so for this, there is another example: count data with over dispersion. That means it violates the assumption of Poisson model. Then we go, for example, hospital visits, insurance claim, or such as, you can go for the negative binomial. So what we can conclude from this slide, start by identifying the type of dependent variable. So first you need to see what is your research interest, and what is your dependent variable. So based on that, you determine appropriate regression model, and choosing the wrong model can lead to misleading estimates and incorrect conclusions. So in case over dispersion present in a Poisson model, then you should move, or you should go to the negative binomial model. Okay, and now I can take the question, I think, from you, because we still have 9 minutes, and when I was little bit nervous that I'm not going to finish within my time, so I went a bit faster, and also I did not answer some question that I'm going to do that now. Yes. Okay. Now you can unmute yourself and you can ask question and I can answer it. I think that would be better. Instead of I keep on reading these things, you can raise your hand and you can ask question. Hello. You can turn the camera on if you want. You can raise hand and I can take one after another questions from you. Okay. It's not possible to unmute ourselves. Oh no, why? I think expert people, can you let them open their, unmute themselves so that they can ask the question? Okay, 1 second. Um, okay, I think you all are unmuted and you cannot ask question. I don't know why, because for me it's very important to hear your voice and know a comment from you. Um, Arifa or Jennifer, can you make sure that you unmute all of them and they can ask question? Can anyone unmute, or just I need to keep on talking? That I really don't like to keep on talking. It's not possible to unmute ourselves. I'm so sorry for that. I don't know. And yeah. Then let me go to all the questions. I don't know how many questions so far came, and I did not address anyone. Okay, so I can start with Elena's question that how can we get rid of heterocadasticity issue? It's a good idea to do the residual analysis or also the robust standard error. And what should we do? Already I answered this question. Yes, and in what unit are these margins interpreted? I don't know which one are you asking, Elena. I really would like to see how can we save all the work done in Stata. Already I said that I'll be including one slide that how to save all those in your work directory. how to export your data or regression output. Is it possible to upload the presentation? Yes. And how can you interpret the pseudo or similar to? Yes. And 6%, does that mean that regression have a low explanatory power? Yes, that means the data explains only 6% variation. That's really not a good uh, model for that data. Can we receive the data set? I used all the data set from Stata website that you just can access from Stata website. And so predicted death are 54 and 77. What number is the person here explains? Okay, let me go back to here. Which one you are talking about? Time to just give you very brief introduction or use of time series analysis and panel model. So we'll be here. We'll then move to the panel that first we'll work with the time series analysis and then the panel data models. I'm not going to explain all these things much now, as already I showed you the time series data structure and the panel data structure. Now, starting with the time series basics, I'm sorry, can you see my slide, all of you? Because I don't know, I can't hear anyone. I can't. Okay, thank you. Thanks. So I feel like, am I doing the right thing? Because nobody's talking. Okay. So now we'll move from cross-sectional analysis to the time series analysis. So far we have done only cross-sectional analysis. So unlike the cross-sectional data, now where we observe many units at a single point of time, time series data follow the same unit repeatedly over time. The examples can be GDP or inflation rate that I have showed you some example before in the first session. Okay, and then time series represent actually unique challenge because the observations are often correlated across time. So before estimating models or making forecasts, we need to understand the concept such as trends or one second, I just want to check one thing. Oh, okay. Yeah. We need to understand the concepts such as trend and seasonality and the stationary. So in the few next slides, we'll see the key ideas first, and then we'll go to how to handle the or set the time series model in Stata. Okay. So first, the time series basics. Already we know that it consists of the observation collected sequentially over time. And here for this purpose, actually today we are going to use the airline passenger data and this data contains monthly number of airline passengers from 1949 to 1960. So before I talk about this, let us um, load our data set and see that how can we fit a model in time series model. So let's again, as I said from the beginning, I did not like to use external data because sometimes there is a lot of other issues when we are using third-party data. So all this data comes from Stata website. You just can remember that when we use data from Stata, you can use either web use or sys use because all these are inbuilt data set. So, and now, one thing that before performing any time series analysis in Stata, we must declare the data structure using TS set. That means that says Stata, this is a time series data. Otherwise, Stata will not be able to analyze. So we then plot the time series. So before going for the model, let us have a visualization to see our data set. Okay. So looking at this graph, we can immediately observe the important characteristics. And what are the things we can see? We use the airline passenger. Okay. First, there is a clear upward trend. You can say that is increasing over time. Numbers increase over time. And the second, there is a strong seasonality because the peaks and troughs are repeating regularly. So you can see there is high and it goes to the peak and then it goes to declines. And so there is a seasonality. And third, the fluctuation becomes larger over time. You can see because the number of passengers is increasing, so it becomes larger, suggesting the increasing variability. These features are common in many econometric and business time series and often determine which modeling approaches and appropriate. Okay, so now, if we set here, in many times is data set actually short-term fluctuations are seasonal movements and can make difficult to identify the underlying trends. So one simple way to reveal a long run movement to use moving average. Okay, so here we compute a 12-month moving average of the airline passenger series. The TS smooth and MA command creates new variable. So let us do it so that you can have a look. So what it does, it creates a new variable called air underscore MA12 and which represent the average number of passengers over the previous 12 months. So then we go to see a visualization again to understand the trend. Okay, we then plot both the original series and the moving average together. So the blue line actually, this blue line is the previous one we have seen already, shows the monthly passenger numbers, while the red line here represent the smooth series, smooth line. And notice that the moving average removes much of the month-to-month volatility and seasonal variation, and the long-term upward trend becomes much easier to see. We can also observe that passengers' numbers generally increased throughout the period from 1949 to 1960, even though there were substantial seasonal peaks and troughs along the way. So yes, we can see that there was always fluctuations. In practice, moving averages are often used as an explanatory tool because they help analysts understand the direction of a series before applying more advanced forecasting methods such as ARIMA models. Moving average also does not forecast future values by itself, but it provides simple and effective way to visualize the underlying pattern of a time series before moving to formal forecasting technique. So here, if we move to the next one, Another important thing in time series data, when you are dealing with time series data, we need a very important terms, we can say, that we often use lagged values and the differencing. But what is lag? Lag is simply previous value of a variable. For example, a number of airline passengers last month is the one period lag of the of this month's values. I have included here an example, but after the explanation, I'll go back there. So in Stata, lagged values are operated with L operator, that means gen L dot, L dot air. So this is the lagged value. And for example, L dot air here refers the previous month's passenger count. And different, so here we can say that if we consider this example, we can see that the number of passengers for the month January, February, and March. So for lagged value for the March would be 120. So just previous months. Now we can see the differencing measures the changes between the consecutive periods. It's calculated as the current value minus the previous value. So what is the differencing for the March? March passenger number was 150 minus the previous one 120. So it's 30. Okay. So also in Stata, how can we make this differentiating with dot? So here d dot and the variable name. So d dot air. This is our first referencing. Okay, so the main purpose of differencing is to remove the trends and make the series more stable over time, properly known as stationary. Stationary is also important because many time series models, including ARIMA, assumes that mean and the variance remain relatively constant over time. So instead, the first difference is created with d dot operator. For example, here d dot air calculates the month-to-month changes in airline passenger. We'll use this lag and difference operator repeatedly when we move to the autoregressive and forecasting model. So let's see how and when we can use them. Yeah. So this is our first model for the time series we are going to set. Here, what is autoregressive model, pair 1, the current values depends on their immediately previous value. And to proceed further, what research question we are having in mind, because we are using the data set, the same data set we are using, the airline data set. Does this month's airline travel depends on last month passengers numbers? So we are going to fit the model to check our research questions. So already, as we have the same data set uploaded, so I'm not going to upload the data set once again, but as you know that we have to tell the Stata that this is a time series data set, and we already did that, but for the safety we can do one more time. Okay, so we have declared the time series data set, and then we have done our first time series model, autoregressive model, or AR1. Okay, so what is AR? Already I said that AR1 model assumes that today's value depends on only on yesterday's, or in our case, last month's value depends, I mean, this month's value depends on the last month's value. The lag coefficient here is approximately 0.96 or here 0.958. So I did approximately 0.96. And highly significant. We can see here our p-value is 0.00, indicating very strong persistence in airline passengers number. And then we are going to see the model, the high R squared value here. This is 0.922. Suggests that last month's passengers numbers explains most of the variation in this month's observation. Okay. Any questions so far? So maybe I'll take the question at the end because I don't want to run out of time. And as I said, that if I can't answer, or if we don't have the enough time to answer the question, you can send me email and I can uh, respond, or also you can write in the chat. So at the end of the session I will answer your questions. Okay. So now, after the autoregressive model 1, or the first model that we have considered, now we are moving to the next one. Okay, so here the autoregressive model with multiple legs called ARP, the model extends the basic autoregressive model by allowing the current value to depend on several previous observations rather than only the immediately preceding period. So here we estimate AR2 model. So P represent the number of leg, meaning that the current airline passenger numbers are explained by passengers number from the previous 1 month and the previous 2 months. Okay, so let's try to run this code and see what happens, and then we can go for the explanations. Oh, I'm sorry. Okay, so this is our leg 1 and this is our leg 2. So what we find here, the leg 1 coefficient is 1.277 and leg 2 coefficient is minus 0.33, you can say. So by looking at this coefficient, we can interpret that current passengers number depend not only on the last month, but also the condition of 2 months earlier. Okay, so both leg coefficients are statistically significant. That's most important. We need to see the coefficients for the first leg is positive and relatively large, and indicating that the passenger numbers remain highly persistent over time. And the second leg is negative coefficient. What does that suggest? It suggests that the observations from 2 months ago also contribute to the explaining the current passenger numbers. Although the relationship is more complex than the simple AR1, notice that R squared here 0.93 in this R2 model. This suggests that including additional historical information provides a modest improvement in explaining the variation. So we can see that other model previously, what was our R? It was 0.92. So very, I mean, it has improved a little bit, 93. Yeah. The key idea here is that sometimes series possess a longer memory, and in such cases use multiple leg can better capture the dynamics of the time series and improve the forecasting performance. Okay, so I already just, this is for a small visualization I have added. So what does it represent here? This is the previous periods, represent the last month's passengers number. This is our current month, and this is 2 months before. Okay, In practice, we rarely know actually beforehand how many legs are needed. So I know that all of you are will be asking me these questions, that how many. But tools such as I mean, there are some tools or ACF or PACS or information criteria helps to determine the appropriate leg structure for the time series model that requires a further going into deeper. That is not the uh, mm, interest of our today's session. I can see some question, but I'm a bit confused that whether I should take the question now or I finish and then come back. Could you please send me the script for the time series data analysis so that I can practice the analysis? Um, I already have uploaded. I don't know who is asking this question. To the, yeah, so I already sent all the script in do file in the same folder. You should be getting. So could you guys check that you get them or not? Yeah. And also in the slides, all the codes I copied, whatever codes are there in the in my do files, but I kept both together in the same. So let us continue. Okay. So now we are moving to the distributed lag model. What does that mean? So for our autoregressive models used the past values of the outcome itself to explain the present. But a distributed lag model is different because it uses the current and lagged values of another explanatory variable. So here, if we ask whether income growth affect the investment growth, or investment decisions often take time. So firms may not immediately adjust their investment when income changes. So the effects can be distributed over several quarters. Okay. So for this, I'm changing the data set because our air data set was not having enough data to show you the distributed lag model. So here we am using another data set. Let's have a look at the data set here. This is quarterly South Africa's West or German macro data, and these are our variables in the data set. You can explore the data set to see what is there, but what we are doing with this data set here, our research question is, does the current and past income growth influence the investment growth? So it gives us data about our income. So in this case, to answer this question, first let us say that it's a time series data set. I'm sorry, again, I copied the wrong code. Okay, so it declares the data set is a time series data set. And to answer our research question, let us make a distributed lag model. And in this select model here, you can see that there are some variables like din, this means growth of rate of interest, and then growth of rate of income. And the current income growth is L0, and L1 is our 1 quarter ago, and L2 is 2 quarters ago. So these are the variables of interest, and we would like to see whether the current and past income growth influence the investment growth or not. So in the model, what we can see here, immediate effect on the income growth on the investment. So for L0, L1, here delayed effect after 1 quarter, and this is already so some predictors affect the outcomes immediately and some appears with a delay. So distributed lag model help us understand how effects are spread over time. So here you can see that how they affect our what is investment decision and how we can. So when when the regressive models, both the regressive model does not capture all the factors, then it could be maybe more valuable to go for the distributed model. And now, the last thing I think from the time series is about our first difference model. Uh, so here, this first difference model actually focuses on changes rather than the levels. And we are going to think about that. We will be here again going back to our airline passengers data set because we can do our analysis. And I tried my best to make sure that we use as less data set as possible. So we're going to use same data set airlines one to show you the first difference model. Here our research question is, does the last month's change in airline passenger help predict this month's change? So when we use the previous data set or the airlines data set to keep no, and you need to declare the data set as the time series data set. Then we are going to see earlier we model the passenger levels directly. Here we focus uh, on the change from 1 month to the next. Fast differencing is commonly used because many time series exhibit trends and are non-stationary. So after differencing, we regress current monthly change or the previous month's change. Here, first we're going to generate the differencing and the lag. So we are going to run the model all together. I'm not doing one by one separate, but here this is our differencing and this is our lag already we have seen before, and then we are going to set the model. Uh, Here again our r squared here is only around 9%, meaning that the most of the months to month variation remain unexplained because yeah, when the model explained only 9% variation, that's really too low. This illustrates an important lesson. Differencing often makes a series of more stable, but it does not necessarily remove all the temporal dependencies. This is naturally motivates the next step in the time series analysis, building more sophisticated models such as ARIMA that can explicitly capture the remaining autocorrelation. Okay, so yeah. And now we are moving to the trained model. That was some basic time series model. I already mentioned that because of the time restriction, the models I did only some kind of basic ones. Now in the trained model, um, we now move to the basic time series models to the trained models. Many time series data sets show a systematic upward or downward movement over time, which we call a trend. And examples include like population growth, GDP, inflation, and so on. And trained models, why we need it, it helps us to separate the long-term movement from the short-term fluctuation. So in this section, we will be learning how to identify the trend and estimate using the regression. So let's move the first one, understanding trends in the time series. So what is trend? Already I said it shows uh, over time, changes over time, like growth, decline, cyclic movement. So again, for this purpose, we are using same data set. So I don't need to upload the data set again. Already data set is declared as time series data set. So I can directly do this to have a visual of this. So many time series. What the graph here shows. The graph clearly shows an upward trend. Already we saw it before coming to this one, the same graph we saw in the time series model. So we also notice the seasonal pattern where the peaks and troughs for each. So I'm not going to explain this one much because it shows this already I included in the time series. So you don't need to I don't need to repeat the same thing again here. So that save time, I can move to the next one. So when we talk about the trend model, the first thing comes the linear trend model. So a linear trend model assumes that outcome changes at a constant rate over time. Here we regress the uh, and with the research question in mind, is the airline passengers traffic increases steadily over time? So we can regress the air with the time. Let's see what we get. And here the coefficient is approximately 2.66 and statistically significant. This means that on average the airline passengers number increased about 2.7 thousand passengers every month during this period. Okay. And what about the model? We can see that R squared here is 0.85, indicating that time alone explains approximately 85% of the variation in passenger number. Therefore, some simple linear trend captures much of the long-term movement in this series. So 80% is covered. However, when we look at the figure, we can look at the figure. See. Okay. Look at the figure. We can see the red fitted line does not follow the seasonal peaks. It goes straight, so it doesn't capture the fluctuations, right? Seasonal peaks. It does the overall upward trend, but not the fluctuations. And this illustrates an important limitations of simple linear trend model. And this they summarize long-term growth, but they fail to capture more complex dynamics in the data set, and that needs to be taken care of. And for to answer that questions or to capture the variability, we can go for the next model in the trend. That's one is called quadratic trend model. So linear trend model assumes that airline passengers number increase by a constant amount each month. However, sometimes the series grow faster or slower as the time progress. To allow the changes, allow for changing growth, uh, rate, we add a squared. So we now here going to consider that going to see whether this fluctuation can be taken care of or captured by the quadratic model. So here the quadratic model allows the growth rate itself to change over time. So again with the research question, does the airline passenger traffic accelerates or decelerate over time? So with the same data set, when we make the quadratic regression, sorry, model, um, so here what we can see, both the coefficient and square time are statistically both. This is quadratic, this is the squared term, and these both are statistically significant. Importantly, the coefficient of the squared term positive, indicating that passengers growth accelerates over time, and that we also can see from the visualization. So let us have a look. It's always better to have a look of the visualization instead of looking at that regression tables. So visually we can see the fitted growth rates. We add a square time, but it's a bit curvy, so it shows the upward trend, but the line is not going very linear or straight line. So that means it capture the seasonal the fluctuation to some extent. Okay. And about the model, when we look at this R square, it's 86% variation in passenger numbers, which is slightly higher than the linear trend model. As I remember, or if we go back, before it was 85%, but quadratic model captures 86%, slightly better. Okay, but not 100%. However, we can still see strong seasonal fluctuation around that range, and therefore, even though the quadratic model improves the long-term fit, it still does not capture all aspects of time series. And for that purpose, we are moving to another one called exponential model. So what is this trend model or exponential trend model does? This model models the growth occurring at a constant percentage rate over time. So here our research question is airline passenger traffic growing at a steady percentage rate? So using the same data set, we are going to set the model, and I'll be going all of them together so that we can get the visualization, or maybe you need to see. Okay. So when we look at the coefficient here for the time 0.01, since the dependent variable is logs, we interpret this as an average monthly growth rate of 1%, and the model we can say R squared 9.90. That means 90% of the variation in passenger numbers, which is higher than both the linear and quadratic model. And now we can also have look at the visualization that's easy to understand and represent. Oh no, what did I do? Let's see. Yep. So you can see that this fitted line is curvier than the previous one, even from the quadratic model. So to estimate this model, Looking at the figure, exponent bends upward and follows the long-term increase in the airline traffic and more closely than the traffic linear trend. This makes intuitive sense because many economic and business variables such as population, GDP, investment, and the passengers traffic tend to grow proportionally over time rather than fixed amount of each period. Okay, and now, because we have seen the three kinds of trend models, linear, quadratic, and exponential, uh, but which one, what does that mean? So linear one assumes linear quadratic, no, linear trend model assume that constant absolute increase. Quadratic assumes that growth rate changes over time, and exponential assumes that constant percentage increase. So here, how to decide the best model? You need to look at the goodness of fit or compare the R square with adjusted R square. You can also do the residual analysis, whether the residuals show the remaining patterns or statistical significance or visual fit also you can say. And the thing is, after going through all these things, you are going to prefer the simpler model where the performance is the similar. So the performance is similar. So that's it about the trained model, and we are having only around 18 minutes to cover the panel data model. So far we have focused on the cross-sectional and time series data. Panel data combines both dimensions by following the same individuals like farms, schools, countries that we already have seen some example. Panel data also allows us to control for unobserved characteristics that do not change over time and often provides more reliable estimates than cross-sectional analysis alone. So in this section, we'll cover the fixed effect model and random effect model. And we also will do Hussman test to see which model we should prefer or choose. We'll also do the difference in difference the model. So now let's go instead of wasting too much time in the theory. Already, I think I have covered this part, so I'm not going to explain panel data again. Let's move to the stata directly. So here for the fixed effect model, panel data follows the same individual over the multiple periods as I already mentioned, and in this data set we are going to use this data set for our analysis. So it comes from a national longitudinal survey of young women aged 14 to 24 years old in 1968. And suppose that we want to know whether the people earn higher wages at their job, tenure increases. So first, what always is better that we use with a simple OLS regression estimates the relationship between the wage and the tenure using all observation pooled together. However, OLS ignores that observations come from the same individual over time. So what happened if we run the pooled OLS or first, and then we compare and we see that what we are missing, why we need to go for the fixed effect model. So I'll not explain the coefficient here already because already we covered the OLS, but when I run the fixed effect model, then I'll compare with the fixed effect models and this pooled OLS model. So here, keep in mind that why not to use OLS only because it treats the observation as independent cross sections, and it ignores the panel structure of repeated observation, and it may suffer from omitted variable bias due to unobserved characteristics. And it also mixes the between person and within person variation. So for that purpose, we are going to use the fixed effect model, and I will come back with this OLS output to compare with the fixed effect model. So here, what the fixed effect model does, now we move to the pooled does. For setting the fixed effect model, we need to first declare the data set as panel data. And that can be done with xt set, and there should it always needs id variable. In our data set is id code, and a time variable that is in our data set is year. You can see here this is id code, and year is our time variable. So if we declare the data set as panel structure, then we make our fixed effect model. Okay, now what we see here, the key idea of fixed model is very simple. We compare each person to themselves over time rather than comparing different people to one another. Think about one woman in this data set. We observe her wages and tenure in several years. The fixed effects model asks always, as her tenure increases, how does her wage change? So by doing so, the model automatically controls for characteristics that do not change over time, such as innate ability, personality, family background, or education completed before entering the labor market. So when we look at this fixed effect model results, we can see that tenure coefficient uh, in the pooled model. So we can go back here. This was our tenure, so which was 0.039. This suggests that an additional year of tenure is associated with approximately 3.9% increase in the wages. However, after controlling the individual effect, when we go back to our fixed effect model, in fixed characteristic using the fixed effect model, the coefficient falls 0.21 and roughly to 1%, or roughly a 2.1% increase in the wages per additional year of tenure. So why did the effect become smaller? Because some of the relationship observed in pool OLS was actually due to differences between people. For example, individuals who are naturally more productive may both stay longer in their jobs or earn higher wages. OLS attributes part of these differences to tenure, creating upward bias. So here, the conclusion is the fixed effect model removes this time variant individual differences and therefore gives us more credible estimate of the tenure effect. Another interesting result is RHO here. Someone asked question, I think this question before, but anyway, I answered in the chat. Which is about 0.63. This means that roughly 63% of the variation in wages is due to persistent individual characteristics rather than short-term fluctuations over time. So here what we can conclude from this fixed effect model and the pooled OLS that tenure still has a positive and statistically significant effect on wages, but the effect is smaller once we control the unobserved individual heterogeneity. So in pooled OLS, we ask, do people with more tenure earn more? And in fixed effect, we ask, does the same person earn more as their tenure increases? This is why fixed effect is often preferred for the panel data structure or analysis. Now we move to another model that's called, when we're dealing with the panel data models, is random effects model. So the random effect model is another way to analyze the panel data. We estimate it using xtreg, and then this is the command. So let's see what happens and what change we find when we go for the random effect model. Okay. So unlike fixed effect here, which only uses the changes within the same person over time, random effects uses both within person and between person information. In other words, this random effect model compares individuals to themselves over time and also compares different individuals with one another. The key assumption is very important here when we are going to deal with the random effect model. Random effect model assumes that the unobserved individual characteristics such as ability, motivation, or family background are not correlated with our explanatory variables such as tenure and age. If this assumption is true, random effect model is more efficient because it uses more information than the fixed effect model. Now we can compare our three models like pooled OLS, fixed effect, and random. So looking at our result, the tenure coefficient here 0.025, this suggests that the additional year of tenure is associated with approximately 2.5% increase in the wages. Notice that this estimate lies between our earlier results. So pooled OLS, we can go back here. Yes, in pooled OLS, it was 0.039, and in a fixed effect model is 0.21, and the next one is 0 in random effect model is 0.25. So this happens because the random effect model combines both cross-sectional differences between individuals and changes within individual over time. We also see RHO here is this is my screen. Yes, 0.56. That meaning that around 56% of the variation in wages is attributed to persistent individual characteristics. So the main practical question therefore becomes, can we believe these unobserved characteristics are unrelated to our explanatory variables? If yes, random effects attractive because the efficient, or it allows us estimate time variant variables. If not, the fixed is usually preferred. So now we are going to see that which one is our best model. So one way of doing so is we are going to do a Hussman test to compare that which model is preferable, FE or RE. For that, we first estimate both model and store the both models. So first, first I'm going to run my FE model and storing that. with the command estimate, store, and FE as FE model. And the next one also I'm doing for R model. And then we'll check with the Hussman test. No, sorry. Okay, so we have stored both the model. Now we are going to compare both the model with the Hussman test. Oh, sorry. Okay. So here, one rule of thumb, you need to look at the chi-square test or test statistics. So you can see it here 326, and the, our p-value is 0.000. So the thing we need to decide how to decide the Hussman test asks that are the individual specific effects correlated with explanatory, yes or no. So here, if the p-value is less than 0.05, then we choose a phi model. But if it's larger or if it's more than 0.05, then we are going to choose RE. Okay. So I'm running out of time. I don't want to explain anymore. All these explanations are there. You can check. Now, so here I made a small comparison between all these things, or how to choose the right model when we have the panel data. Pooled OLS, it ignores the panel structure and may produce the biased estimate. So, and here we may choose the fixed effect model, and uses the within person variation and control for the time invariant characteristics. And we also see in random effect model uses within and between person variation and more efficient if the assumption holds. So with the Hussman test, we can see that which model is preferable. If the p-value is smaller than 0.5, we use FE, and if it's larger, then we use RE. And this is the last thing, I'm sure, but maybe I'll be taking 2-3 minutes more to finish this. So did panel data in difference using the same data set, if we see that did the wage changes different after 1980 for the workers with more than 12 years of schooling. So what we did, what we do in differences is a method to evaluate the impact of policy or intervention treatment. The idea is to compare how output change over time for a treatment group relative to control group. So in this example, we create a simple difference setup using this Nils work panel data set. So here we are going to create treatment group and also control group. So after with yeah so this I after creating this, we are going to make set the fixed effect model with the interaction done. So how did we make the treatment group? Here, treatment group is defined as the worker more than 12 years of schooling, and the period and the post period actually defined as observation from 1980 onwards. And we also estimate the model with the fixed effect model, and let's see that what happens in our uh, uh, regression output. We notice that here the treat is omitted this treat group is omitted from here. This happens because the education group is time invariant for individual, and fixed effect already controls all the variables that do not change over time. The coefficient of interest is interaction pattern. So this is our interaction. We did post and treat here in our output, and the coefficient is approximately 0.029 and statistically significant. Since the outcome is a log wages, we can interpret this approximately 2.9% higher risk outcome for the treated group after 1980 relative to the comparison group. So the main lesson in this difference in difference is the interaction term captured the differential change over time between the treatment and comparison groups. Some of you ask, that's all, I think we are over time. Some of you ask about that, how can we report or how can we save our work? So here I try to give very brief things. Already I said that you can save in the do file. That's always recommended because you will not be doing the same work repeatedly many times. So always it's better to do your work in do file where you can change always. You also can this way I'm showing that how to export the graph or save the graphs in the device already in your work. So if we use the same data set, sys use auto, and we do the scatter plot, then you can export the graph by using graph, then export, and with this command your graph will be saved already in your existing drive. So let's see here, this will be saved. If I go back to my drive for year 1, I will see that this is scatter plot price MPG already saved in my day 1 folder. Check for that. And you also can export the regression tables by outreg command. For example, if I run a regression model, but for that I'm not sure I have already installed this, but most of you most probably don't have. So it's always better to install this package, otherwise it won't work. So first I'll do all the 3 together, but you can do one by one. So it's installing, though I installed before, so it will take a couple of minutes. And then again, this diagram has been saved as OLS doc. We can see, I can go back to my here. So OLS doc, the output of this regression model is saved here. It takes a bit time. Yes, you can see the output has been saved here. So and cancel. And another good way of doing, always you can start a log file when you start working in Stata, so all your work will be saved in the log file. And with this command you can open this, or you can directly open that I showed you beforehand from file and then log open. But because I already opened the log file, so I have log, I now close, but that means my session is ending, so I'll be closing that. And you can open the do file, a new do file from here, or sorry, from do file editor. When you click on it, click on this place. This is my existing one, but I can also open a new one by clicking here. I'm not going to use this, already opened one here, new, and you can change the name, you can say whatsoever you want to do. I'm not going to open another one, and you can save it. And the last one, what I want to say, that already we did all this command today. You can select all of this and you can transfer to a do file. So I'm selecting all my commands from the history window, and then you right click and you can send selected do file editor. So when you click on it, then a new do file will be created, and then you can change name and you can you can save it for your future reference. Okay, so this is my previous one that's already uploaded, and you can say that all whatever we have done, all the codes are here. Then you can do some kind of edit. Always is better idea to write the version so that it will work in the other version. If you put at the top 19.5, and then you can say, okay, this was day 1. Remember that when we put this star sign and then write Stata, take it as a comment or note, so it will not execute. So day 1 training, you can say our next code was loading data set, loading data set, and so on. So if I want to close this one, or I can save it, you can click here, save, and you need to give one. Then you can say, maybe I can use training and save it, and it will be saved in your existing drive work directory. So that's all. I think now I will stop sharing, and I can take your question. I can see some questions are there. We are run out of time, but I need to check that. Continue now. Thank you, Sabiha, for work.